Yeah, we can see. Yeah.
Okay, sounds good. Okay, thanks once again. So yeah, hello everyone. So I guess all of you would have been enjoying the talks so far, and you must be learning a lot of new things. So yeah, so as Dr. Arun said, I work in area of natural language processing, and today I'm going to and I would first of all like to thank the organizers for inviting me to give the talk in this workshop. And so today I'm going to talk about one of the recent research areas that I've been working on, and this is called as legal NLP. So legal NLP is a new and emerging area, and a lot it's kind of a new in the sense that not much work has been done in this area, and a lot needs to be done in this area. And I'm also kind of relatively new in this area, and I've been working in this area for almost like 1.5 years. And in this presentation, I'm going to talk about some of my thoughts about how to make progress in this upcoming area. And in addition, I will be talking about two of our recent works in legal NLP domain, basically. So before I proceed, I just want to put a disclaimer there that I'm not a lawyer and I do not know any legal intricacies. So pardon me if I say something which is technically incorrect in the legal parlance. But nevertheless, I actively collaborate with law professors, and this helps me to understand the legal domain. All right. So in this presentation, I will follow a grounds up approach, and so let me start with the fundamental question: why do we need special NLP techniques and tools for legal text? So in recent years, there have been several developments in the NLP field that have advanced the state of the art by almost tenfold. And as many of you might be aware of the magic of transformers and the revolution that they have brought in. So the question is, why can't we use those advancements directly for legal text? So in this, in couple of upcoming slides, I'm going to outline some of the main reasons for doing this. So by the way, when I say legal text, I mean legal documents such as court judgments, contracts, bail documents, written statutes, etc. So any document dealing with legal matter, or any document stating or describing the law, essentially. Right. So the first and foremost challenge with legal text is that legal documents are usually super long. So for example, if you look at court judgments, typically on an average, these would have like around, let's say, 3,000 tokens. And this is in contrast to much shorter documents used to train conventional NLP models. So long documents are challenging to process as information is spread over the entire document, and it needs to be retained and recalled appropriately depending on the task. And as some of you might be aware of BERT and transformer based and many other transformer architectures, and you might be knowing that there is a limitation of 512 tokens as the input to these models. So legal text cannot directly be fed into a transformer model. So we need to explore more advanced architectures. And what is really more fascinating is that if you look at lawyers, they can process these super long documents with, I mean, by lawyer, I mean an experienced lawyer, they can process these super long documents with such an ease that it is really, really fascinating. And the idea is, if something could be done with deep models, something similar could be done with deep models as well. That is going to be really great. So legal documents use natural language. For example, they might be in English or Hindi or some other regional language. However, these documents use legal domain-specific lexicon. So commonly occurring words in natural language could have specialized meaning in legal parlance. So the use of specialized lexicon and different semantics associated with words makes pre-trained neural models ineffective. So, for example, if I try to use a transformer-based model which has been trained on like the regular English text, it may not work. It usually doesn't work well on the legal text. And moreover, in India, we have a kind of a multilingual society, right? So every state, at least at the district court level, uses a regional language or the local language for the legal document. So that kind of makes things even more complicated. So just to give an example, here is, if you look at, here's an excerpt from a legal document. It's a judgment document, basically, from a Supreme Court case. And here you can see that it is using some specialized terms basically, right? For example, events and assessors of respondent. So these are not, I mean, these, I mean, if you show these to laymen, even they would have a hard time understanding these, right? So, I mean, then you can imagine like what would happen to in case of deep models, basically deep learning models. So legal documents, especially in like common law countries like India, are highly unstructured and noisy. So they might have like grammatical mistakes or spelling mistakes because many of them are manually typed. So this makes it challenging to extract information, right? And moreover, many of these documents are scanned and text, and you need to extract text from these using some kind of OCR or, I mean, those kind of techniques. So that further introduces noise into the text or the data, basically. So just to give an example, so in this court judgment, you can see that you have a regular text going on, but in between there is a point which is not part of the main text mentioned, right? So this is kind of separate point. So if some model is processing this document, then how does it take this point into account? It is kind of not clear, basically. And this kind of thing is fairly common in like court judgments, basically, right? So another challenge with legal domain is that it is further subdivided into many subdomains corresponding to different laws. So for example, there might be documents corresponding to criminal law, there might be something to do with let's say income tax law, competition law, and so on and so forth. So although some of the fundamental legal principles are common, the overlap between different subdomains is low. Hence, a system which is developed on one law, for example, let's say on income tax law, may not directly work on another law. So for example, on criminal law. So there is a problem of domain shift. So the models need to be robust against, I mean, the models that you train should be robust, that they are able to work in different domains as well. So currently, most of the state-of-the-art predictive models that you see, I mean, most of them are coming from deep learning techniques, are essentially black boxes. So for example, for a given input, it gives a prediction without any reason for that prediction. Right? However, for wide acceptance by legal practitioners, the models that you develop for legal text, these need to be explainable, as it is essential to know the reason for a decision in the legal domain, right? So, I mean, the lawyers or the legal practitioners are going to be the end users of these models, right? So if model is giving some prediction and if it doesn't tell why is it giving that prediction, so the lawyers or the legal practitioners may not trust the model, right? Sometimes some predictions might go against the intuition, but they might be valid predictions, but still, if there's no explanation, then the lawyers may not trust the system, basically, right? So explainability is kind of a very important in case of legal domain. And lastly, the legal text is country specific, as many of you might have guessed, like different countries have different laws. So the techniques developed for one particular legal system may not generalize for legal system in another country, right? So, I mean, so for example, if you want to develop something on, let's say, European Union law, you develop a model which works very well on European Union law. If you try to use that same model in Indian setting, it usually doesn't work so well, basically. And we have experimented with such models, and that's what we have also observed. So these are some of the fundamental challenges with legal text, and this motivates the development of new techniques for processing legal text. And so some of these techniques are, as I'm going to outline as we go further in the talk. So but before I go describe any of those techniques, let me also outline like the challenges that I just described. What is lacking there, basically? What is preventing us from developing models that work well on the legal text, right? So I think following things are lacking and that impede the development of legal AI. So firstly, there is a dearth of legal corpora. As many of you are aware that recent developments in many of the communities, for example, computer vision community, owes its success to development of specialized corpora, for example, like ImageNet. And for any ML area to make progress, there should be basically data, right? So, I mean, you train the models on data. It's all data driven, basically. Same is the case for legal domain as well. We need annotated corpora for development of techniques and systems basically. However, the challenge with legal corpus is that annotating these is not easy, right? So you basically need legal experts for annotations, and this also motivates the this is one challenge. But suppose if you all have some annotations which you manage to get using legal experts, you may not get them in kind of huge quantities, right? So you will have small number of these annotations. So this kind of also motivates the development of some techniques like zero shot learning or few shot learning, which can generalize from even less number of examples basically. Now, secondly, the recent developments in NLP have been possible due to presence of pre-trained models, which have made transfer learning quite easy and possible. However, legal domain is yet to have such models, right? So though recently some approaches like legal transformers have been proposed, but a lot more needs to be done basically, right? Moreover, we have in our experiments, we have seen that legal transformers do not work well on legal text, due to variety of reasons that I just mentioned. And so some specialized architectures are also need to be kind of investigated and developed basically. So lastly, in mainstream NLP, you see the availability of NLP toolkits like such as Spacey, Stanford NLP, and so on and so forth. So these make life easier, enabling to carry out low-level tasks such as like tokenization, lemmatization, name entity recognition, code reference resolution, and so on and so forth. However, such toolkits do not exist for legal domain, and given that legal text is very different, you need some specialized toolkits. So recently we have been working on developing such toolkits. However, due to time constraint, I'm not going to talk about that. Maybe I will talk about that in some future talk. As you understand, like we need something which can readily process the text and help us to develop more advanced applications. Okay? So let me also outline some of the typical applications in the legal NLP domain, basically. So and just to point out, this is not an exhaustive list. These are some of the applications, some of the popular applications actually. So for one of the common tasks that is done in legal AI is prior case retrieval. So the task here is that given let's say a legal document, you would like to retrieve all the prior cases which have similar facts and similar setting basically, right? And this is very useful for lawyers essentially. So if a new let's say a new case comes to a lawyer with certain facts, he or she would like to retrieve all the past cases from the database, which have kind of similar setting with respect to facts, and so that they can frame their case according to the decisions that were given in the past cases. Okay? And then another task is summarization. So given that legal documents are super long, right, as I mentioned earlier, so you would like to have some system which could summarize so that legal practitioners could quickly go through the summary instead of reading the entire long documents, right? And then there is the task of argumentation mining. So as you know that in legal judgments or in legal documents, there are arguments and counter arguments between like between the lawyers basically going on, right? So the what is really interesting is like can we automatically extract these argument structures? So by argument structures, I mean things like premise, some kind of conclusion, relation between main and counter arguments within the discourse basically, right? So if these could be extracted automatically, then these could be useful for different tasks, for example, judgment prediction, for example, right? And then there is the task of information extraction and retrieval. This is kind of like you want to extract some kind of information from a document, or you want to retrieve certain types of documents, legal documents essentially. So that's another. This is kind of similar to like standard NLP tasks, but in the legal domain basically. And then there is the task of segmenting the documents, but more in terms of semantic units. And then there is a task of legal judgment prediction, where given a, let's say, a judgment document, you want to develop a system which will predict the final decision of that of that case basically, right? So these last two I'm going to talk in more detail further in the slides. So before I proceed, Does anyone have any questions so far?
If you have any queries, please raise your hand so that we can unmute you and you can ask the questions. Otherwise, you can even drop it in the chat box.
Yeah, though I may not be able to monitor the chat, so maybe you might have to tell me.
We'll do it.
All right, so I don't see any raised hands or any questions. So, okay, so let me proceed further. So I'm going to talk about like one of our recent works, which is on legal judgment prediction. And this is called as ILDC for CGP. So ILDC stands for Indian Legal Document Corpus for the task of court judgment prediction and explanation. So let's try to understand why do we need judgment prediction, right? So essentially, why we need artificial intelligence to assist in this task, right? So in highly populated countries, especially like India, there exists a vast number of pending backlog of legal cases that impede the judicial process. So according to a recent statistics, there are around like 40 million pending cases in various courts in the country. So now you can imagine that the scale at which we have this backlog. And this backlog is due to multiple factors, including like unavailability of competent judges, and then the whole process takes up the whole quite a lot of time. So therefore, a system that is capable of assisting or augmenting a judge by suggesting the outcome of the ongoing court case will be useful for expediting the judicial process, basically. Right. So, however, an automated decision system is not tenable in law unless it is well explained in terms of how humans understand the legal process. Hence, it is necessary to explain the prediction list, right? So in other words, we would like to have a system that not only predicts what should be the final decision of the court case, but also it tells how it arrived at that particular decision. So kind of gives the explanation for that decision. Okay? So let me talk about the CGP task that we propose in this work. So given a legal document or a proceeding, the aim is to build a AI system that is capable to determine the outcome of the case. Okay? However, this task would be just a legal judgment prediction, or LJP. So this the first box that you see. But as I mentioned earlier, an automated decision system is not tenable in law unless it explains how the model reaches that decision, essentially, right? Therefore, in CGP task, the task is to explain the decision as well by determining the important sentences that lead to that decision. So this is the explanatory part. So essentially, we have two kind of subtasks within this task. One is the prediction part, where you want to predict the final decision of the case, whether it is accepted or it is denied. I mean, the appeal is accepted or denied. And then you want the system to also give the explanation why it arrived at that decision. Right. So in our case, it kind of points out the important sentences that led to that decision, as I'll show in further slides. Just as just a disclaimer, as I mentioned earlier, also, so the task is not to replace any human, but to kind of assist a human judge, basically, right? So let me outline the main contributions before I go into details. So we create a ILDC corpus, or Indian Legal Documents Corpus. And it's a corpus of, as the name suggests, a corpus of Indian legal documents containing around 32,000 documents, legal documents. And in addition to that, we provide a subset of ILDC documents, which are annotated with explanations corresponding to the court decisions. And then we introduce a new task, the basically court judgment prediction and explanation, or CJP for short. Which, as I said, has two subtasks: court judgment prediction and explanation of the prediction. So one thing you should note is that the requirement for explanation also puts the restrictions on the type of technique that could be tried for judgment prediction, right? So in the CGP task, cold explanations are not provided in the train set, and the task expects that the trained algorithm should explain the predictions without requiring any additional information during training, right? So it's kind of unsupervised explanation, sort of unsupervised, giving unsupervised, giving explanation in an unsupervised fashion, basically. Right. So we basically develop a battery of baseline models for the CGP task, as I'm going to show later. And we perform extensive experimentation with the state-of-the-art machine learning algorithms for judgment prediction tasks. So we develop a new method for explaining machine predictions, since none of the existing methods could be readily applied in our setting. And we compare the model explainability results with the annotations by legal experts using automatic matrix, as I'm going to show later. Just a spoiler alert. So we observed that there is a significant difference between the predictions by the algorithms and the experts, right? So as I'm going to show this later. So in the past, there has been a lot of work in the area of legal judging prediction. So in previous work, for example, Chalkidis et al. In 2019 proposed a neural model for legal judgment prediction and released an English legal judgment prediction dataset containing around 11,000 European court cases. And then Strickson et al. In 2020 prepared a test set of UK court cases and employed classical machine learning models for the task of prediction. And in 2018, Xiao et al. Released a large-scale Chinese data set for the task of judgment prediction, and it contains around 2.68 criminal cases. And several approaches have been proposed, have been put forward for the task of judgment prediction, notably like hierarchical BERT, multi-perspective biofeedback network, and topological multitasking. For explainability, Zhong et al. In 2020 presented a QA-based model using reinforcement learning for explainable LGP task, in which the model aims to predict the appropriate crime by asking relevant questions related to the facts of the case. So yeah, there has been a lot of work, but there has not been much work in regard to the explainability part, essentially. So so how is CJP is different from the existing work, basically? So CJP is firstly, in case of CJP, we require predictive algorithms to explain the outcomes by highlighting the important sentences that point towards the outcome. So for evaluation, we provide a separate test set with gold annotations. In the previous task, for example, LGP, facts are strictly provided as input to the model or algorithm. Whereas for CGP, we provide the complete unstructured document without the metadata and, of course, without the actual judgment in the end. Also, the ILDC corpus for the task of CGP is the largest legal corpus for Indian setting, containing around 34,000 judgment documents. So let me talk about how did we create the ILDC corpus. Here you can see the pipeline for the LDC dataset. So in the first step, we extracted all the Supreme Court cases spanning from 1947 to 2020, April 2020, from a website called Indian Qanun. So Indian Qanun is a legal search engine for Indian law. It provides access to millions of central law and judgment Indian judgment documents, basically. So as a next step, we pre-process the documents, removing the meta information that is not relevant to the core document, basically. So in SCI case proceeding, decisions are written towards the end of the document. So these end sections directly stating the decision have been deleted from the documents in ILDC, since that is what we aim to predict. And for each case, actual decision label has been extracted from the deleted end sections of the proceeding using regular expressions, basically. So another challenge with Supreme Court SCI or Supreme Court of India case proceedings is the presence of cases with multiple petitions. So here, like where in a single case, multiple petitions have been filed by the appellant, leading to multiple decisions. So consequently, we divide the ILDC documents into two sets. The first set is ILDC single, And as the name suggests, it has documents where there is a single petition and thus a single decision. And then there is ILDC multi, where we have multiple petitions, but the decisions might be different across these different petitions. And and also like for certain cases where we have multiple petitions, but the decision is same across all the multiple petitions, those are also part of ILDC single. So, and as you can see, ILDC multi is kind of a superset of ILDC single, since it has multiple appeals leading to different decision or same, different decisions basically. And the binary, so the binary label for ILDC multi, so basically for every ILDC multi document, there is a label, whether it is accepted or denied. So it is, we take this as accepted even if a single appeal or petition was accepted in this judgment basically. And then we basically took these documents and we call them ILDC expert from the test set, and which was common for both multi and single splits basically. And these were given to 5 legal experts basically, and the experts were requested to predict the judgment and mark the sentences that they think are explanation for these judgments basically. So each document was annotated by 5 experts in isolation using web anno framework, and annotators could assign ranks 1 to 10 to the sentences selected as explanation. Higher rank indicates more importance of that sentence towards the final judgment. And this data set, as I said, is called as ILDC expert basically. So let's look at some of the ILDC statistics. So as I said, like we have 3 different data sets or sub data sets maybe: ILDC multi, ILDC single, and ILDC expert. So the average number of tokens in these pretty long documents. And so, and as you can see that the validation and test splits for both multi and single data sets are kept same. And we, as I said earlier, we annotated 56 cases with explanations. And since each document consists of annotation by 5 legal experts, and given that the size of these documents are like they are usually long, these set of 56 documents is kind of a good enough data set test set size for evaluation purposes. Though we are still in the process of increasing the size of this annotated data set essentially, and hopefully in future we'll release more annotated documents. So let me now look at the some of the temporal and the bias aspects of the ILDC data set and the task as well, and the CGPE task. So let's discuss the temporal aspects of ILDC first, and how we try to minimize the basically the bias propagation. I'll come later. So firstly, as you can see that the train test validation split was not based on any temporal consideration, and the reason for that is that when we want the system to, what we want the system is that it should actually work with standard features of the judgment pronounced in relation to various legislation by different judges across different temporal phases. Also, to be able to use the set features to decipher the judicial decision-making process and successfully predict the nature of order finally pronounced by the court, given a set of facts and legal arguments. So, in this setup, if we do not consider the temporal aspect, or if we alternatively, if we consider the temporal aspect, the system is likely to fail in any practical application, since in futures the laws might change, right? So if it is trained on certain set of laws coming in certain time period, then the system may not generalize for future things basically, right? So and that's the reason that we took this step of not basically we randomly sampled the documents from across the entire timeline basically, right? And we did not have any temporal considerations there. And so regarding the bias mitigation aspect, So we randomly sampled the documents and did not focus on any particular domain of cases or any particular domain of cases coming from a particular law, basically. Right? As a pre-processing step, we remove all the meta information from documents like name of the judges, name of the appellants or petitioners. The anonymization with respect to the judge's name is necessary, as legal experts pointed out that judges identity can sometimes be a strong indicator of the case outcome. It is noteworthy that according to the legal experts, if we had not done the same, we could have had higher prediction accuracy. And the subjectivity associated with a judicial decision-making process may also be controlled in this way, since system focuses on how consideration of facts and applicable laws are supposed to determine the outcome of the case, instead of any individual bias on judges' part. So we conducted both quantitative evaluation and qualitative evaluation by case studies for the judgment prediction task. We noted that our case studies, we noted from our case studies that although experts agreed on decision for most part, some differences were observed. So the sources of confusion were mainly due to differences in linguistic interpretation of legal language in the document by the experts. For quantitative analysis, we calculated the accuracies of experts with respect to the gold labels, which are the actual judgments given by the judges, as you can see on the left. Note that though the decision predictions are close to 100%, none of them are able to achieve a perfect score, right? So they are not full, they are in the 90s, but not, it's not 100%. We observed that pairwise inter-expert agreement for judgment prediction was sometimes as low as 85.7%, and as high as 94.6%. And we also calculated the Fleiss kappa for all the 5 annotators, and it was around 0.82, which points towards a higher inter-annotator agreement. Similarly, for the task of explanation for the prediction, we conducted both quantitative and qualitative analysis. The qualitative analysis revealed that expert 2 and 5 often use bare minimum reasoning leading to the final judgment instead of looking at the exhaustive set of reasons, and did not always cover both the substantive and the procedural aspects. By substantive aspect are basically the sections of the law applicable, and procedural aspects are the jurisdictions by the lower court. On the other hand, expert 1, 3, and 4 perform holistic reasoning for the decision. They look at both substantive and procedural aspects of the case. And the difference among them are largely due to consideration and non-consideration of the factual sentences. For quantitative analysis, we use various metrics like Rouge, Blue, Meteor, Jacquard similarity, and overlap metric to automatically determine the expert agreements. Here we only provide the results. As you can see, we only provide the results for Rouge L score, and I will point towards the paper where we have more metrics basically. So as you can see, user 3 and user 4 have significant amount of agreements in what sentences of documents they choose as explanation. However, sometimes it could be as low as 0.608, as you can see in the diagram on the left, basically. And this points towards the subjectivity and complexity of the task. So on the so coming to the actual prediction via models, we conducted a battery of experiments for the task of judgment prediction. So we experimented with sequentials model with sentence embeddings coming from Send-to-Vec architecture, glove embeddings as well. We conducted experiment with transformer-based models like BERT, Roberta, and XLNet. And since these transformers are limited by their quadratic complexity of self-attention and can only take it, up to 512 tokens at a time, we experimented with the first 512 tokens and the last 512 tokens, and noted a significant difference between the performance in the two basically. And a difference is due to the fact that many semantic cues towards the actual decision are present at the end of the document. We obtained the best prediction performance of like 77% using hierarchical XLNet with bidirectional GRU. However, our best performing model is still far behind the average expert's prediction accuracy, which was around 94%. So this points towards like a lot needs to be done, and the task is quite complex. So here is the best performing model, the diagram for the best performing model. So so basically what we do in our best performing model, since the documents are super long, we divide them into chunks, basically, as you can see in the bottom. So these chunks are basically contiguous sequence of 512 tokens, right? And these chunks go as input to XLNet, which is a transformer based architecture. And from these XLNet, we get the representation for each of the chunk. This we obtain via the CLS embedding of the output. And so these representation or features of each of the chunk are fed into a bi-directional gated recurrent unit model, basically bi-group model, right? And then we obtain the representation from, and we use two-level bi-group. And we obtain the representation for each of these hidden units of the upper layer bi-group, and we concatenate them and then feed them to a MLP via basically using a dense layer. Okay? And the output of this gives the prediction, the final prediction of the case. Right. So, and for the explanation, so the explanation method that we use is based on representation erasure technique. So the idea here is that we mask a chunk embedding at a time, and we calculate the mask probability of the label after feeding the mask input to the model. And we compare the mask probability of the to the unmasked probability to determine the relevance or importance of that chunk. And we do the so basically what the idea is that we remove, let's say we remove this chunk, and then we calculate the probability of the prediction, and we compare this with with this chunk in place, and we see if this chunk is really important, then there would be a significant drop in the prediction without the chunk, basically, right? So that's how it gives an idea whether this chunk is important or not. And basically we do it at two levels, basically, right? Since our model is hierarchical, which has two levels like bi-group half and XLNet half, so we do this representation erasure at two levels, basically. So so for the model at the top, which is like the bi-group, so we have representation, I mean we have the bi-group representation of the document, and we calculate the relevant scores of each chunk using the procedure I just described. And the next step is to do the similar procedure for the XLNet part, where we mask the sentences and compare with the unmasked instance of the input to determine the sentence-wise relevance, basically. So there, as I said, we have two levels of representation erasure. One is at the bi-group level, where we mask chunks, and one is at the XLNet level, where we mask sentences, basically. Right. So yeah. So then we kind of visualized. So basically, as you see, and we are using transformer architecture here, and these transformer architecture uses attention mechanism in its different layers, basically, right? So we compare, we visualize the chunk relevance score and average them out for the documents that contain the same number of chunks. And so we compare this with the occlusion is the technique I just described, the representation erasure technique, and the attention is attention coming from the transformer. So as you can note that both occlusion and attention scores share similar trend, basically, right? So here, as you can, so an interesting observation is that this basically they kind of give high score to the chunks which are coming later in the document, basically, right? And this is in agreement with our earlier observation that most of the semantic and syntactic cues to make the final decision are present at the end of the document. And this is like just one graph here, but we provide more analysis in the paper. I'm going to tell about the link to the paper later, basically. And then we look at the results for the task of judgment explanation, and then we note that overlap. So as you can note, the overlap scores, overlap min scores for machine versus experts is as high as 0.83, and whereas scores for blue and meteor are kind of low, basically. And then we compare the Legel scores for machine explanation with the expert agreements, and note that Legel score of 0.44 is quite behind actually the lowest Legel score of 0.61 between user 5 and user 2. So yeah, and we have more analysis in the paper basically. So yeah, so basically I will I'm not going into too much details here in the interest of time, and for more details I would refer you to this paper, and we also release the corpus and the entire, I mean, the code for all the models basically, and you can play with the corpus and the models and experiment and perhaps develop better models than what is there basically. So you can scan this QR code and get the link to the paper and the GitHub repo basically. So yeah, before I go further, any questions so far?
If participants having any questions, you may raise a hand or else you can type on chat box.
All right, so if there are no other questions, then I'll just I'll briefly outline one more of our recent work basically. So so this is a task of semantic segmentation of legal documents. So the idea is as follows. So essentially, as you know, that legal documents are super long, right? So to process them automatically, it would make sense to divide them basically, right? And as you saw in the previous slides, that we were dividing them randomly into small chunks, basically contiguous chunks, basically, right? So rather than dividing them into contiguous chunks, it would make sense to divide them into units or chunks that are semantically and topically coherent. So basically, right? So basically, within a chunk, it's going to be about one topic, right? So just to give an example, here is a legal document here. I mean, it's, as you can see, it's a pretty, pretty dense there, right? What we want to do is we want to divide it into small chunks or basically labels, and label each of these chunks. And so, for example, you want to, let's say, extract, let's say, the facts of the case, as you can see here, right? This facts basically, right? And then some, let's say, some issue or arguments, right? So this would make the processing of documents much easier. And these labels that we assign to each of these chunks are called as rhetorical roles, right? So we divide the document into these chunks and assign a label to each of these chunk, and it's called as a rhetorical role. So this task is called as rhetorical role prediction. So given a document, divide it into chunks and label each of these chunks with some predefined labels, which are called as rhetorical roles. Right. So we concentrated on 9 main rhetorical roles. So these are like facts of the facts. So these are about like what the facts of the case are, the sentences which correspond to the fact. Then there is arguments, which are like different arguments given by the lawyers in the case. Then there are statutes, which are different laws. Then dissent, if there is some dissent by the judge in the case. And then there is some kind of precedent, like what kind of precedent is it? Like the precedent, is it like the precedent which is followed, or existing precedent, or is it some kind of overruled precedent, and so on and so forth. And then there is usually the like Supreme Court cases have some ruling by a lower court. So these are given by given the label ruling by lower court. Then the ratio of decision is basically the rationale which is given for the final decision. And then the ruling is the final prediction for the judgment document, which is the final decision. And then there is also a none label, which corresponds to none of the above, basically. So for this task, we develop a novel model, basically. So the idea here, I mean, intuitively, the idea here is that the document is within a document, we have different rhetorical roles occurring, right, for different sentences corresponding to different sentences. So these rhetorical roles tend to maintain some kind of inertia, and they do not change abruptly. So for example, I start with, say, sentence 1 or sentence, and so it has, let's say, one rhetorical role, for example, facts. So there is a tendency to maintain this role or the label like facts for a couple of more sentences. It's not going to abruptly change to some other label, basically, right? So that's the intuition that we want to make use of, basically. So what we do, we propose is a multitask learning setup. So there are two tasks that we are predicting at the same time. So there's a shift component and a RR prediction component. So what we want to do is we want to first predict whether there is a shift in the label, which is this is the auxiliary task, right? So we want to predict whether there is a shift in the label, like a shift in the rhetorical role label. And if there is a shift, then that should inform the RR prediction part that, okay, there is a shift. So it should kind of update its probability about the possible labels that could happen. So for the shift prediction part, we basically, so we fed the input sentences to both the components. So you have sentences S1 to Sn, which are fed, and then we obtain some kind of representation for each of the sentences using some kind of a sentence BERT architecture. And these are fed to a BiLSTM architecture. And then on top of that, we have a conditional random field based architecture, which kind of gives a sequence prediction for shift. Basically, for at every position, we have a binary prediction, which tells whether there is a shift or not a shift at this particular sentence. And for the main prediction, our rhetorical role prediction part, we have a kind of a similar architecture. We take the sentences, obtain the representation using sentence BERT, and then pass these as input to the BiLSTM architecture. And then these are combined with the predictions coming from the shift part, concatenated with them basically, and then these are fed to CRF. And at every step, we are predicting one of those 9 labels that I showed earlier, basically. Right? So one of these, I mean, whether it's a fact or precedent and so on and so forth, basically. So that's the overall model or the architecture. So here are some of the results. So so MTL is our model, and we had like 2 different versions. I'm not going into details there, but as you can see, it performs better than the, let's say, the standard BiLSTM model or BiLSTM CRF model, or even the legal BERT model, basically. Right? So there's a substantial difference between these. So because in the interest of time, I'm not going into details of all these models, and you can refer to the archive preprint that we have released regarding this these models essentially. Right? So yeah, I would stop there so that we have some time for questions as well. So so in nutshell, basically, I described the legal NLP area, and it's kind of a new and upcoming area, and a lot of work needs to be done from grounds up in this area. So the field is just starting, and so there is a lot of opportunities for research there. And in this talk, I presented like the use case for legal NLP area for legal judgment prediction. And in this work, we created a new corpus, and I would encourage you to play and research with this corpus. All the data and code is available. And so as we saw from the results, the models for legal judgment prediction are still in their infancy and showed significant difference compared to the legal experts, basically. Right? So there's a lot of scope for improvement. And then in the later part of the talk, I introduced the task of rhetorical role prediction, which is basically about dividing the document semantically into chunks so that each chunk is topically coherent, basically. Right? And then I also showed a very very briefly showed the model, the new proposed model, the multitask learning model, which makes use of the label shift information to make the prediction. And I didn't go into details, so I pointed towards the paper, and you can refer to that paper for more details. So yeah, I would stop there. Thanks a lot. So yeah, any questions?
Participants, if you have any questions, you may raise. Even you can chat.
So if you have any questions or you have any comments or anything?
Yeah, thank you, sir. This is a very nice session actually. So it's a complete and practical application-oriented sessions event. Hope it will be. Even if you participants will be contact you later also. If you hope you never mind.
Yeah, sure. Yeah, please. I mean, feel free to contact me. Yes.
Yes, sir. We will share anyhow. We will share with your permission. We will share your presentation to the participants.
Yeah, sure.
Later they will contact you.
Okay, sure. All right. So okay, thanks everyone. So I hope you enjoy I mean the rest of the sessions in coming days, and all the best for everything. Thanks.
Thank you, sir. Thank you, sir. Thank you. So participants, if you don't have any questions, we will wind up the session for the lunch break. We'll again gather by 2:15.